Hello, my name is Elizabeth Bennett, and this is my presentation for the fourth lab in Physics 2211. The purpose of this lab was to compare the observed x and y position of a weight on a vertical ideal spring to the modeled x and y position data of the same weight on the same spring. The models used in this lab are GlowScript code used for the model data and a video analyzed with tracker for the observed data. The overall results of the lab were that the observed position data roughly follows the model data, but it follows closer in the y direction than in the x direction. Additionally, the total change in energy was found to be zero. The fundamental physical principles of this lab consists of Newton's second law, which is that the net force is equal to the change in momentum over the change in time. This also encompasses the velocity update formula, position update formula, and spring force formula that are shown on this slide. The other fundamental physical principle is the energy principle, which states that the change in the total energy of a system is equal to the work done on or by the system plus the change in the heat of the system. This principle relates to kinetic energy, spring potential energy, and gravitational potential energy that are seen on the screen as well. In the experiment, the system is the spring, the weight, and the earth. The surroundings consist of nothing. Because of this, the total change in the energy of the system is zero, so it just equals itself, which can be calculated as the kinetic energy plus the spring potential energy plus the gravitational potential energy. The initial conditions of the experiment are that the weight begins at rest and at the position negative 0.197 meters in the x direction and negative 0.833 meters in the y direction, based on the axes and origin defined in tracker. In the GlowScript code, first the mass of the weight was defined to be 0.402 kilograms as measured. The initial position is what was previously described, and the initial velocity is zero as the weight begins at rest. The modeling begins when t equals 0 seconds, and the position is updated every 1/210th seconds. The gravity constant is defined as 9.8 meters per second squared. The spring constant was found to be 6.83 newtons per meter, and the relaxed length of the spring was measured to be 0.123 meters. The compressed distance of the spring was calculated by determining the difference between the position of the weight and the base of the spring minus the initial uncompressed length of the spring. Then the energies associated with the system are calculated based on the formulas previously given. The initial energies are the calculated energies using the initial conditions. The force of gravity acting on the weight is given by the mass of the weight times the gravity constant in the negative y direction. The force of the spring is given by the spring force formula given earlier. The net force is equal to the sum of these forces. This net force is used to determine the updated velocity, which is then in turn used to calculate the update position. The new compressed distance of the spring is calculated based on this new position of the weight. Based on the new velocity, position, and distance of compression, the energies of the system can be calculated. When the initial energy amounts are subtracted from these new energy amounts, the change in each of the energies is given. This repeats at each time point until the while loop finishes. Here we can see the model data in blue versus the experimental data in red. As previously stated, they follow each other for the most part, with the y direction data being much closer between the two. Based on the energy graph, energy is conserved within the system, meaning that the change in total energy is zero. The first what if question is asking if the energy principle is satisfied. It is satisfied because the total energy is always zero and the sum of the other three types of energy equal the total energy. The second what if question asks to make predictions of the period of the spring based on the x and y position data. The period shown by the x position data is 1.75 seconds, while the period shown by the y position data is about 1.5 seconds, showing there is a difference of around 0.25 seconds in the two models. These errors could be due to drag force, errors in tracking when I was clicking the spring's position, and possible motion in the third axis projecting from the screen that we could not visualize in 2 dimensions.